All right. Hi, everybody. What you have in front of you is your exam review. That exam review covers everything we've done to this point in the semester, as well as this last couple of topics we're going to do before the final exam. The exam review is optional, though if you choose to complete it and turn it in on or before the last day of class, which I believe is the 22nd, it is worth 5 points of extra credit onto your final exam, and you get to use the review on your final exam. So, you should do it, right? My recommendation to you is to take your time, do it well, be thorough. Don't try to sit down and do it all in one setting. Piece it out over several days so that you don't get tired and get sloppy. Because the more thorough you are with your review, the more detail you include as to how you're doing things and what to do and how you know what to do, the more helpful it'll be for you on the final. The final format is basically going to be the shorter version of the review with different numbers. And you may see some possible repeated questions where it's oh, this is the same question from the review. I just copy this in here. Just need to do a good job. The idea here is that I want to take this exam from being a memorization exam, where having locked an entire semester of math is pretty rough, and turn it into a preparation exam, where if you do a good job on this review and you're really thorough and detailed on it, you get to the exam and should be pretty good, should feel pretty good. So I know that the thing is long. It's long intentionally because I want to give you guys, practice and coverage, and I'm giving it to you basically 2 weeks before it's due, so you don't have to worry about scrambling to do it at the last minute, though we won't have a ton of class time to work on this. So I want to give it to you early so you have time to kind of, do a couple pages here and there, or maybe a chapter at a time or something, whatever. Everybody feel good about the review? Okay. Next up, the chapter 15 test that you guys just took is graded and entered. I also put in doubled high test scores for everyone. If you are someone who'd rather do a test retake instead of do the doubled high test score, you need to let me know probably by the middle of next week for us to find a time to do your retake. That final week before exams, there's 2 days where there's no classes that meet. So we got to kind of get that. If you're thinking of doing that, you need to make a decision pretty quick, and we need to act on that and get that figured out. If you just are going to take the doubled high test score, it's in and entered, so you don't have to do anything if that's what you're choosing to do. Most people take that option. Everybody okay there? Okay. To end the semester content-wise, we're going to do 2 final topics on sequences and series. We're going to do the sequence topic today. It's 45 minutes-ish worth of material. It's not tremendously complicated, as the most difficult stuff is built on ideas that we've already done this semester, which is nice. That the complicated things are basically things we've already done, so not a big deal. It's some new vocabulary and some new notation, but the toughest things are going to be fairly simple. And then, so we'll have that. We'll have a homework assignment based on that lesson and a Delta Math based on that lesson. And then we'll do series next week. We'll have an assignment based on that and a Delta Math based on that. And those are your last assignments, other than the Chapter 15 review, which I think is set for Sunday to be due. Those will be the last assignments due before the final exam. All of that I think I've scheduled to have due this Sunday or the following Sunday. Or I'm sorry, next Sunday or the following Sunday. I think or maybe everything is due next Sunday because we don't have any classes the week after. That's probably it. Or we have just the one X day or something. Or maybe this is the B class. Maybe we have Monday and the X day then. I can't, or Tuesday and the X day. I think we have like the Mondays off for graduation or something. But I think we're basically, we're almost done. So I think all the homeworks are due the following Sunday. Everybody's okay there? And the complete schedule to the end of the year is up on My Notre Dame. So if you go to our class page, and take a peep at that, it has everything through to the final exam up there. So if you miss, really simple as to what you missed, it's all up there throughout the end or up to the end of the year, or up to the start of exams anyways. Everybody cool there? The last thing, so in grading your chapter 15 tests, there was some curious methods used to answer by some people answering questions that looked unlike anything that I had ever taught you guys. Make me rather suspicious about people using AI or something on their exam or on their test. So as a heads up that for the final exam, I will be asking for your cell phone before I give you an exam. Like no cell phone, no exam. And if you're in a class of mine in the future, the same policy will hold. Like I'm not going to give you a test until you've turned in your cell phone. So just if you've been relying on that as a tool to kind of get you through things, we're taking that is going to be more heavily policed here going forward. And I want to let you know before the final exam that do a good job on your review packet, do a good job on your half sheets going forward, that you can have those things. I don't mind giving you some help, but you got to still do it yourself kind of thing. Okay? All right. I think that covers all the little incidental things. So our last two topics here are going to be this, what I'm calling Chapter C, because in the digital book, this isn't a written section. I just took this from another textbook, pre-calculus textbook we own, as I think we're going to transition into a traditional textbook for this course next year. So this is just kind of me getting a chance to look through that textbook and kind of get a jump on that. All right. So this first section, our first topic in Chapter C, is going to be on sequences. So we should start by just defining what is a sequence, Mr. Kulik. What do you mean by that? Well, a sequence is just a type of function, but it's a special type of function where the inputs for this function have to be positive whole numbers, like 1, 2, 3, 4. And the outputs, though, could be any real number. So you can't input into a sequence things like a half or -3 or 0. The only inputs that work are your counting numbers, 1, 2, 3, 4, 5, etc. Everybody okay with that? So one way that you can describe a sequence is just by a list of its outputs. So for example, we could talk about the sequence 5, 10, 15, 20, 25. That's a sequence. You could describe the sequence like 2, 4, 8, 16, 32, ... 2 to the k, ... So 2 to the k is kind of the general form of all the terms in the sequence. That's called like the kth term. And notice the ... there at the end. What's that kind of telling you about this sequence? keeps going on forever following that same pattern. Notice the first sequence, does it have a dot, dot, dot? No. So that sequence is just those 5 numbers. Everybody okay there? You might also describe a sequence as a set. So if you look at example 3, that's the set of 1 over k's, where k is the numbers 1, 2, 3, 4, 5, etc. So that set would contain the things like 1 over 1, 1 over 2, 1 over 3, 1 over 4, etc. Another infinite sequence going on forever because the values for k go on forever. Is everyone okay with that? And then kind of in the most generic sense, we can just describe the sequence as like, give it some name, like we can call this sequence like a sub k. So the first term in our sequence we call like a sub 1, and then second term a sub 2, and then a sub 3. Here we're not telling you what the values of these terms are, just rather that it's some sequence. And here are the the names for the terms. So these outputs from our sequence are called the terms of the sequence. So like, for example, in the first sequence there, the terms are 5, 10, 15, 20, 25. And then we have the term number, that's like the input to the sequence. So the first term in that sequence is 10. So the term number for 5, the first term is 5. So the term number for 5 is 1. The term value for the first term is 5. Everybody's okay with that? So each term has a term number, like what place is that in the sequence, and a term value, what is the output from the sequence? What is the actual number? So for example, I think I said, if I use the first example, if I look at 10, if I call this sequence like b sub n, b sub 2 would be 10 because it's the second number in the sequence. Is everybody okay with this idea? This should look a lot like function notation, right? Like I might say that f of 2 is equal to 10. Like when I plug 2 into my function, I get 10 to come out. So this sequence notation with the subscript is basically the same thing as the function notation. Instead of having the variable in parentheses, the variable is the subscript. Does that feel okay? So much like a function where you can think of inputs and outputs as ordered pairs, like points, we can think about a sequence as points. So again, if you're looking at that first sequence, 5, 10, 15, 20, 25, the points would be like 1, 5, 2, 10, 3, 15, 4, 20, 5, 25. Does that feel okay with kind of vocabulary and notation? It's important that, in a way, the hardest part about this is just getting used to the new language, the new vocabulary, the new symbols, the new way of writing things. But it's expressing the same old ideas that we've been hammering for a couple of years now. So when we talk about sequences, what we're going to do now is build up a vocabulary of ways to kind of describe them. One way that we might classify these sequences, what adjectives we might use to describe them, is we might want to describe them based on the number of terms. If we do that, there's really 2 classifications. There's sequences that are finite and sequences that are infinite. If I look at our above examples, example 1 is finite because it contains exactly 5 terms. There's a fixed number of terms in our sequence. It's a finite sequence. If I look at the second sequence, that is an infinite sequence because the dot, 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 the number of terms goes on forever. There's infinitely many of them. We'll call it an infinite sequence. Mr. Salik.
Sorry.
It's okay. Sure. Does everybody feel okay about the difference between finite and infinite? Pretty straightforward, I think, right? Now, when we talk about writing a sequence, we can write a sequence as a list of numbers like we've done up here, but oftentimes that's pretty inconvenient and not very helpful if we're going to ask questions about the sequence and what happens in the future and all that kind of thing. So one of the things that we'll want to do is be able to write a formula to describe the sequence. And there's really two different ways to write a formula to describe a sequence. We can have an explicit formula where the formula is based on the term number. So for example, in the second sequence up here, the explicit formula is just, would be like a sub k equals 2 to the k, right? When I plug 1 in for k, I get 2. That's the first term. When I plug 2 in for k, I get 4. That's the second term. When I plug 3 in for k, I get 8. That's the third term, et cetera, et cetera. You see that this formula describes the sequence there exactly in a really compact way, right? We'll talk later about how to write explicit formulas. I may write an explicit formula here going on in the future, kind of, like a little ad hoc. I'm very good at this because I've been doing mathematics for a long, long time. You will not be. I will tell you later on exactly the types of sequences I'd expect you to be able to write an explicit formula for and how to do that for those types of sequences. I will write explicit formulas for things that would not be, if they're not obvious to you and maybe you can only see it afterwards, that's okay. So don't panic on that. And the other type of way we might write a formula for a sequence is called a recursive formula. Now, a recursive formula is based on the previous term. So if I look at that first sequence, I notice that 10 is the previous term 5 plus another 5. Or I notice that 15 is that previous term 10 plus another 5. Or 20 is the previous term 15 plus another 5. Or 25 is the previous term 20 plus another 5. So we might write the recursive formula for this as the previous term plus 5 So when we write a sub 1 or a sub n minus 1, that's just like a symbol for the previous term. That's all that means. So if I want the fifth term, the previous term is the fourth term. If I want the 26th term, the previous term is the 25th term. Fairly simple idea, although the notation is a little bit confusing until you realize, oh, that's all that means. And then if you're given a recursive formula, you also have to give a starting place, because without a start, you can't build a recursive formula, right? Like if it's the previous term plus 5, it's like, great, where do I start? What's the start at? You got to give the start, because you can't add 5 to something you don't know to get it going. All right. Let's grind through some examples now that we've talked a little bit about what a sequence is in general. So find the first 6 terms and the 100th term for the sequence a sub k, where a sub k is k squared minus 1. So if you look at this, this is an explicit formula because it's just based on the subscript, the term number for the sequence, right? So if I want the first term, I just plug 1 in for k. Well, that gives me 0. If I want the second term, I'm going to plug 2 in for k. That gives me 3. If I want the third term, I plug 3 in for k. That gives me 8. If I want the fourth term, I plug 4 in for k. That gives me 15. If I want the fifth term, I plug 5 in for k, and that gives me 24. If I want the sixth term, I plug 6 in for k, and that gives me 35. And then if I want the 100th term, I just plug 100 in for k, and that's going to give me 9,999. Again, you could type those into your calculator. You don't have to do them in your head. You know, like, again, math teacher, been doing this for a long, long time. I'm very, very good at it. It's not hard for me to do it in my head. If it's hard for you to do in your head, that's okay. That's why the calculator's there. But is everybody okay with the idea here? We're just plugging these in for k. Just like in Algebra 1 when you encountered function notation and you get used to plugging things into a function, right? Exact same idea. Now let's say we have the recursive formula and we want to do the same thing. So we're told the first term is 3, and the second term is going to be the first term plus 2. That's what it says in the formula. So that would be 5. The third term, well, I'm going to need the second term plus 2. So that would be 7. The fourth term is going to be the third term plus 2. So that's 9. The fifth term is going to be the fourth term plus 2. So that's 11. The sixth term is going to be the fifth term plus 2. That's 13. But what if it asks me for the 100th term? Can I do that straight away with what I've done so far? No, right? If I have a recursive formula, if I want the 100th term, that means I'll have to found the 99 terms before it, right? Barf. That's pretty gross. In general, I would not ask you to do that. The power of the recursive formula is it's a very, very simple formula to write. But to actually work with, it's not often that helpful because to get a specific term out of the sequence, you need to have computed all the terms before it. Now, if you're a computer, no big deal, right? A computer can do 1,000 calculations like this in like a second. For a human being, this is kind of a hassle. Now, for this particular sequence, because of the nature of it, we can actually do this without having to calculate the 99 terms beforehand. Because if I look at the values in the sequence, 3, 5, 7, 9, 11, 13, what do you notice about all those numbers? They're all the odd numbers, consecutive odd numbers starting at 3, right? So let's say if I start with, let's start at 1. What's the first 100, or what's the 100th odd number? So from 1 to 100, there's 100 numbers, right? Half of them are odd. So the 99 should be the 50th odd number, right? So I add another, like, if I go then from 101 to 200, 199 would be the 200th, or would be the 100th odd number, but we started at 3 instead of 1, so we actually need one more odd number after that, so it should be like 201. Now, I would not expect you to common sense your way through that, but like, this one doesn't look so bad. But in practice, you really need the 99 of them beforehand. We kind of cheated there and basically used the explicit formula in a way to go straight to the answer we wanted. Is everybody okay with what I did there? Another way that we might classify our sequences is based on their limit. And there's really two types of classifications we'd make for sequences based on their limits. We'd say either the sequence is convergent or divergent. so to do that, what we'll do is we'll take the limit as n approaches infinity. So if that limit exists and is a finite number, we say that sequence converges. If that limit is infinite or doesn't exist, we'll say that that sequence diverges. So let's do a little bit of practice, kind of getting used to this idea. So if we're checking to see, it says determine whether the sequence converges or diverges. If it converges, give the limit. So what I need is an explicit formula to do this with. Well, in this first example, I'm given the explicit formula. So if I have the fraction 1 over n, and that denominator is getting infinitely big, right? What is the value of that fraction going to go to? Where is it heading towards? So we start off with like 1 over 1, and then it becomes 1 over 2, 1 over 3, 1 over 4, 1 over 5. As that denominator gets bigger, that value of the fraction is decreasing, right? What number is it decreasing to? Well, it can't be a negative value because it's going to be a positive number over a positive number. So what's the smallest non-negative number it could go to? 0, right? That's the smallest. If you have a positive divided by a positive, the smallest possible result you could get is 0, right? Now, the other way you could have thought about this is if I look at 1 over n, that looks a little bit like a rational function to me, right? And I know to do the n behavior of a rational function, that's essentially the limit as n goes to infinity. So to do the n behavior for a rational function, I need to look at the degree of the numerator and compare it to the degree of the denominator, correct? The degree of the numerator is not 1, 0, because there's no variable. The degree of the denominator is 1, because it's n to the first. Everybody remember that? Or they, after I say it, they're like, oh yeah, okay, I got that. When the degree of the numerator is less than the degree of the denominator, we had a horizontal asymptote at y equals 0. Hence the limit is 0. And if you look before, I have the rules for the end behavior of rational functions written down below this, but we'll keep on going here. All right, if I look at example B, notice that I have not been just handed the explicit formula there, right? Which is a bummer. So we're going to have to write our own explicit formula. So let's look at the single fraction. What do you notice if I'm comparing the numerator and denominator of these fractions? If I'm just comparing the numerator to the denominator for each of these fractions here, what do you notice? Okay, just in a single fraction though. In each fraction, the numerator is 1 more than the denominator. You guys all see that? I have 2 over 1, and then 3 over 2, and then 4 over 3, and 5 over 4. So my explicit formula I'll write is just n plus 1 over n. I would not expect for you to come up with that on your own, but after I write it, you should be able to look at it and go, yeah, that checks. Right? If I put 1 in for n, I have 2 over 1. If I put 2 in for n, I have 3 over 2. If I put 3 in for n, I have 4 over 3. What's the degree of the numerator in n plus 1 over n? 1. And the degree of the denominator is 1. So if the degree of the numerator equals the degree of the denominator, we have a horizontal asymptote at not 0. Y equals leading coefficient over leading coefficient. So the leading coefficient of the numerator is 1. The leading coefficient of the denominator is 1. 1 over 1 is 1. So you had the right answer, Brooke, for the... In this case, yes. All right. If I look at the next one, again, I'm not given an explicit formula. Yes. Sure. So I'm going to have to write my own. If I look at the numbers 2, 4, 6, 8, 10, what do you notice about all those numbers? They're even. Yeah, that's the better answer. How do I, what is the, what's true about all even numbers? How do I know if a number is even? What's my test? If I'm like, is that number even? If it's divisible by 2. So each of these numbers should be 2 times something, right? In fact, it's going to just be like 2 times n, because 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6. Is everybody okay with how I came up with that? Again, we haven't talked how I'm doing this so quickly and easily. I'm just kind of talking through anecdotally. We'll systematize the writing of explicit formulas here in a few minutes. So if I look at 2 times n, and n is getting infinitely big, this is no longer a rational function, right? Because it's not a fraction. What's going to be happening to n, or what's going to be happening 2 times n as n gets really big? Okay, let's think about it this way. If I look at the graph of 2 to the n, it just looks like this, right? This is the n behavior that we're interested in as n's going to infinity, right? If this is like the n-axis and this is like the 2 to the n-axis. What is that n behavior going to? Positive infinity, right? So the first one we would have said is converges because it goes to a finite number. The second one converges because the limit is finite. The third one, though, diverges because the limit is infinite, even though we can find it. And the last one, they were nice again and gave us the explicit formula. But let's look at this sequence. It just goes -1, +1, -1, +1, -1, +1. When n goes to infinity, is it going to be 1 or -1? Why do you say +1? But it's going -1, +1, -1, +1, -1, +1. How do I know which one it's going to be when n goes to infinity? Can we tell? No, there's no way to tell. You just can't tell whether it's going to be -1 or +1. So what are we going to say in this case? The limit, Mean Girl fans, does not exist. You've been waiting your whole math career to say the line. Now you've gotten your opportunity. We say the limit does not exist. Because you can't tell what it should be. It's just going back and forth from -1 to +1, -1 to +1. What's infinity going to give me? How should I know? I can't tell. Doesn't exist. Everybody's okay? All right. So again, I wrote down the rules for rational functions. Basically, the first case we'd say is those cases are convergent. The limit or the sequences are convergent. In that third case, where you have to do the polynomial division, the sequence is going to be divergent. Everybody's okay with that? And I wrote down the rules there if you want to look at it, if you want them again. But they're the same rules we had for rational functions, which is nice that we're recycling this idea from before, right? All right. Let's run through a couple more examples because this is kind of a new skill. So what do I notice about the sequence in A? It is a rational function, right? So I can just use my rules from above. The degree of the numerator is 1. The degree of the denominator is 1. Since the degrees are equal, I do leading coefficient over leading coefficient, which would be 3 over 1, right? Or just 3. So this is, we'd say, converges. Is this still going okay for everybody? You're with me? We're just using those same rules of rational function end behaviors here. So again, I have another rational function, right? The degree in the numerator is 2. The degree in the denominator is 3. Since the degree of the numerator is less than the degree of the denominator, the limit should be equal to 0. Always 0 when the degree of the numerator is less than the degree of the denominator. Oh, so that's converge also. All right, our last example. Again, rational function. Degree of the numerator is 3. Degree of the denominator is 2. If the degree of the numerator is greater than the degree of the denominator, then we have to do that polynomial division thing, right? Guess what? We don't care what the result is. All we need to say is diverges, right? We don't need to say whether it's going to be positive infinity or negative infinity. It'll be one or the other. In this case, I can tell looking at it, it's going to be positive infinity, because when you do the polynomial division, you're going to get like 1n plus something. Because the slope is positive on that, it tells me that the end behavior is positive infinity. But like I don't need you to do that much. Just recognize it's divergent. You can write divergent. Because that third case, where the degree of the numerator is greater than the degree of the denominator, where you'd have to do the polynomial division, it's enough to just recognize, oh, it's that one, that's the divergent one, and be done. Everybody's okay? All right, so let's get down to brass. Yes, sir. Yeah, let's get down to it and start talking about writing explicit and recursive formulas for sequences. So there's 2 types of sequences that I would ask you to write explicit or recursive formulas for. Those type of sequences are arithmetic and geometric sequences. So our key property to recognizing an arithmetic sequence is that consecutive terms of an arithmetic sequence, if I subtract them, I get the same number every time. We call that number the constant common difference, and we abbreviate that with the letter D. So if I wanted to, I can write the explicit formula for an arithmetic sequence using the formula a sub 1 plus n minus 1 times d. Or I could write the recursive formula by writing a sub n equals the previous term plus d and listing the first term. So those are basically my formulas that I'll use for an arithmetic sequence. Everybody okay with that idea? Okay, let's do some examples, then we'll talk about the geometric. I'm only going to do example 1 because example 2 is more than I want to get into in this kind of a setting at this point in the year in this kind of a class. So I'm told that the following sequences are arithmetic. We want to find the common difference, the 10th term, a recursive formula, and an explicit formula. I'm actually going to find the 10th term as the last thing that I do, because I'm just going to use the explicit formula to go straight to the 10th term, so I don't have to generate all this stuff in between. So the first thing I want to do, it tells me it's arithmetic, but I'm going to check anyways. So what I'm going to look for is to see if going from -6 to -2, can I add or subtract a number to get there? What number would I add or subtract from -6 to get to -2? You add 4. Okay. If I go from -2 to +2, I would add 4. To go from 2 to 6, I would add 4. From 6 to 10, I would add 4. That shows me that this is arithmetic, and it tells me that common difference is 4. Everybody feels good there? Okay. To write the recursive sequence, that is the previous term plus d, which is just 4, and the first term, which I know is -6, because that was given to me. Everybody okay with that? Mr. Kulik, this is a piece of cake. And then to write the explicit formula, I know the explicit formula has to look like this. So we've already identified the first term is -6, and the d is 4. And if I simplify that down, if I want, I'd get just like 4n minus 10. So now if I want to find that 10th term, I can just plug 10 in, and I get 30 very easily. I think that's simpler than going and keep adding 4 a bunch of times and make sure I've done it enough times or not too many times. Let me just use the explicit form and cut straight to the chase. If I look at this, though, this explicit formula for this, what kind of a function is this? Looks like an mx plus b to me, right? That's a linear function. So when we think about arithmetic, you want to think linear function, where the d is like the slope. You're just writing the equation for a line, basically. That's the whole idea. Everybody okay with that? All right. For a geometric sequence, the key property here is that if you divide consecutive terms, the quotient should be the same every single time. We call that a constant common ratio, and we abbreviate that with the letter A. So our formula to write our explicit sequence or explicit formula is just the first term times r to the n minus 1. And our recursive formula is the previous term times r, where we've listed the first term. It's okay there. Let's look at a specific example. Again, I'm just going to do one of them because the other example is more than I really want to get into. So if I try to make this arithmetic, now it tells me it's geometric, but if I wasn't sure, if I try to make it arithmetic, look what happens. Already, I know that it's not arithmetic because I'm not adding the same number every single time, right? Now, what if we try to make this geometric? So in geometric, instead of adding or subtracting the same number, we're going to be multiplying. So what would I multiply 3 by to get to 2 or to get to 6? 2. And from 6 to 12, and 12 to 24, and 24 to 48, 2 again. So that tells me it's geometric because it's a multiplication problem, and that the r is 2. Piece of cake, Mr. Kulik. So far, this is real easy. So now we'll write our recursive formula. So that's the previous term times r. And we need to list the first term. That's it. Okay, no big deal. Just plug in numbers into a formula. I like this. The explicit formula is the first term times r to the n minus 1. Well, the first term we know is 3. The r we know is 2. So we're done there. You can do this all day long, Mr. Hulik. So to get the 10th term, that's going to be 3 times 2 to the 10 minus 1. 2 to the 9th is 512, and then times 3 is 1536. Again, I can do that in my head rather quickly. If that's something you need to type into a calculator, no problemo. You should do that. And our final example, the most complicated question that you'll get here. We're going to make this real easy, though, by using our calculator to help us with some of the heavy lifting. If you have your graphing calculator with you, I invite you to take it out to follow along. Oh, before we do that, though, one more thing. If we look at this formula for our geometric sequence, what type of function is that? Where the variable is in the exponent. We just studied them. It's exponential. So when you see geometric sequences, you should think exponential function. Sorry, I wanted to say that first before we go on to this final example. All right, so the last example says the second and fifth terms of a sequence are 3 and 24 respectively. So we know a sub 2 is 3. We're told a sub 5 is 24. Find the explicit and recursive formulas if the sequence is arithmetic and then if the sequence is geometric. Okay? So what we're going to do here is we're going to recast this problem as like an XY table where the X's are going to be like the term numbers and the Y's are going to be the term values. And if I want a explicit and recursive formula for an arithmetic sequence, we're going to start by finding the explicit one first. Everybody's okay there? And to do that, we're going to use our calculator. So what I'm going to do is I'm going to enter those points, those x and y's, into my calculator. So I'm going to press Stat, and then from the Edit tab, I'll pick the Edit command. And I'm going to enter into L1 the x coordinates, 2 and 5. And into L2, I'm going to enter the y coordinates, 3 and 24. Pause here for a moment while people are following along can catch up. Okay. Yeah. So you move your cursor up to so it's on the title, and then you press clear and the down arrow, and it'll wipe the entire column for you. You're welcome. Okay. Once I've got my data in, I'm going to exit out to the main menu, so second, and then the mode button. And then I'm going to press the stat button again. And this time I'm going to go over to the calculate tab. And because we're looking for an arithmetic function, which is really just, arithmetic sequence, which is basically just a linear function, I'm going to pick the linreg command here, command 4. So I type my x's into L1 and my y's into L2, so that's all set. So I'll just hit calculate. So what this says is that a sub n is equal to 7n minus 11. That's my explicit formula. Everybody's okay there? So to get my recursive formula, I need d. Well, the d is going to just be the slope from my explicit. So there's my d. And I need the first term. Well, since I have the explicit formula, I can calculate that really easily. That's just plugging 1 in for n. So there's my recursive formula. Easy peasy. The calculator did the hard part for me. If I didn't use my calculator, what would I have had to do? I'd have to plug in 2 for n, and then 3 for a sub n. And then again, I'd plug in 5 for n, and 24 for a sub n, and have to solve that system. Yuck. If I don't have to do that by hand, I'd rather not. Just let the calculator handle it. But that's basically what you would do if you're forced to do this by hand, which you would not be forced to do in this class. For part B, it wants us to do it geometric. So again, I'm going to start by getting the explicit formula. I've already entered my data. Remember that in a geometric sequence is like an exponential function. So to find that explicit formula, I'm just going to do stat, calc tab, and then I'm going to scroll down to the 0 command and do the expreg, exponential regression. My x and y list are still the same, so I'll hit calculate. So this tells me that a sub n is equal to 0.75 times 2 to the n. That's my explicit formula. Now the r is just the base of this exponential. That's easy enough. And the first term I can get just by plugging 1 in for n. Now I have everything I need to write my recursive formula. And I'm done. What do you guys think? Again, I think this is the most complicated problem, but we use the calculator and what we had already learned about regression equations to simplify it enormously. That's a huge time saver for us. We love that. So your assignment here is going to be based on this homework here. I'm going to ask you to do 1 through 31 odd. So 15 or so problems is probably enough. And the next class we'll have a delta math based on this lesson to work on. If you finish both of those, you can work on your review during that time also. Or if you have questions from your review based on stuff you did at home, you could ask during that time also. So I am trying to find some time during these next week or so where you can do some review stuff or ask questions about your reviews individually. But we're going to kind of keep inching along on this topic. The class after that will do series and then have a delta math day for series. And again, chances to ask about your review if you get stuck on stuff as we go. I'm going to drop in a digital copy of our exam review here into the OneNote, probably by the end of today. I won't post a key for the review until the last day of class. So the last class day after I've collected the reviews, I'll post a key. So if you're studying and you realize, oh no, I did a very bad thing and screwed up this whole section here, that you have something, to study that a little bit closer because your review might not be that helpful to you. But I will have that. You can certainly ask me about whether you're doing stuff right or wrong, and I'm happy to look at what you're doing before that. But I think it's important that you're kind of doing the review yourself and kind of like really forced to struggle bust your way through the stuff that you don't feel good about so that you know what to include on your review in terms of like helpful instructions to yourself about like why you're doing something or what you need to do or how you knew to do something. And there's no way to do that by just copying my answers. You got to do it yourself. So I'm holding that stuff back until after it's turned in, and then I'm happy to share with you, but we'll wait till then. Okie dokes. Okay, how's everybody feeling? It's all right? Okay. If you have late stuff that needs to get caught up on, you're running out of days to do that. So if you had grand plans of like, I'm going to get all this homework done and caught up with, you are running out of time on that. So I would put my foot on the accelerator pedal there and make sure I'm try to get caught up as soon as possible, because it's not like we're not going to continue to do anything in this last 2 weeks here. So if you had grand plans of getting caught up on a bunch of stuff, the time is running low. So I would make that a high priority here over the next couple of days and try to get caught up on as much as I can. Okie dokes. Yes.
When is the latest?
The lates. I would say that last day of class, I'll accept things up to that last day, but like, let's try not to wait to the very last day to turn them in. Even if you're like, well, I'm going to do all of it, like as you go, send me some updates so we can kind of check things in as we go, rather than waiting all till last minute. But I would say that past Friday the 22nd, end of school, even if it's after the end of school, like on still on the 22nd, but if it's at 2:46, not doing it. Just so you know. Yes, sir. Everybody okay with that? Fair enough? Unless we've spoken, I granted you special exception for turning something in past that. I would say that no bueno.